Okay, so lecture 12, Calc 2. Before I continue with integration by partial fractions, let me go back to college algebra and the concept of completing the square. So if we are given a quadratic like this, and well, this quadratic doesn't have to be irreducible, but for us, it's irreducible. First thing we do is we factor a, because we have to complete the square here inside. Then inside we add and subtract half of this. So this b over 2a squared is b squared over 4a squared, right? So this thing that we have added and subtracted is in fact b over 2a squared, or it is this guy here divided by 2 squared, this guy divided by 2 squared. So this is in fact like this, b over a divided by 2 squared. Now when we do that, this and this, they give me this, they give me x minus b over 2a squared, and the rest remains. Now this is what we call completing the square. So here we have something which is squared plus some, or plus or minus some constant. Okay, now you will see where this thing is used. So let me give you some examples of this completing the square. Well, let's do the one that we started, I gave you as an example. First of all, let's say, well, when you complete the square, you will see that it is, in the end, if that constant is minus some constant, that is, that was irreducible. I mean, that was reducible. Otherwise, it is irreducible. So let's just complete the square, regardless of being irreducible or not. So what I said is divide this b, positive or negative, divided by 2 and square it. So dividing this by 2, I will get 1. 2 divided by 2 is 1, 1 squared is 1. So here I will add plus 1 minus 1 plus 2, right? So this is the b over 2a squared. And a, look, a is 1 here. Most often we have 1 here, so you don't worry about a. Now these 3 give me x plus 1 squared. 2 minus 1 is 1. So I'm done. This equals this. So completing the square in a sense means that turn this into something squared plus or minus some extra thing, which means in fact we are trying to see how far is this thing from being a complete square. This thing is plus 1, say, how should I say that, more than something squared. Okay, so this guy here, x squared plus 2x plus 1, is a complete square. And this guy here is plus 1 away from being a complete square. So yeah, that's a good way to say that, how far it is from being a complete square, which is this thing. This is a complete square. This is plus 1 away from being a complete square. Okay, so let me write another one for you. One that is not so trivial. Oh, I should change these things. And number 2, so let's write a 3 here. And my minus, say, minus where is that? 5x plus not 2. 2 is, well, 2 is okay, well, that's something else. That's 6, 7. Okay, so b over 2a is what? b over 2a is minus 5 over 2, and a is 1. Now this thing squared is 25 over 4. So I add and subtract. And plus 7. Now this is a complete square, and it is x minus, in fact, this thing, which is 5 over 2 squared. And this is plus 4 times 7, 28, 3 over 4. Okay, so this expression or this quadratic function is this much away from being a complete square. Okay, so it is this much away from being a complete square. That's it. One way we can say it. And another thing is, when you have negative here, then b is negative. So, and negative squared is positive. So that's why it doesn't matter whether it's positive or negative. This is always positive. This is thing. But inside you will see that you will get minus, because that this thing was minus 5 over 2. Okay, so these are two examples. Since I don't think you encountered any quadratic that has that the coefficient a is other than 1. If it is just factor that coefficient out of that and then continue. Now, let me keep this thing, and as the third example, I need this thing, so let me write it over here. Now, the thing is, how can I find this integral? 1 over x squared minus 5x plus 7 dx. So, first thing I do is I complete the square in the denominator, and that is x minus 5 over 2 squared plus 3 over 4. So this is like x squared plus something, right? X squared plus something. So let u be this inside, x minus 5 over 2, and du will be dx. So this is equal to 1 over u squared plus 3 over 4 du. Okay? So I turn this into an integral, which is something squared in the denominator plus something else squared. Okay, now you might say this is not square. Yeah, this is in fact square root of 3 over 2 squared. So it is something squared. It doesn't have to be integer, just some number. So let me continue this one. In fact, this has a general form. So what is the general form of this integral? So the general form is this. So let's write it as a note. The general form is integral 1 over u squared plus a squared du, right? So if I let u be tangent theta, a tangent theta, not just tangent theta, a tangent theta, right? Then du is a times 1 plus tangent square theta d theta. So if let me erase this thing, and so if I plug in here, I will get a times 1 plus tan square theta d theta, and denominator will be a squared tan square theta plus 1 plus a squared, sorry. So this is, let me write it again so you see what's happening. Denominator is a squared times 1 plus tan square theta d theta, right? So this is in fact 1 over a d theta, which is 1 over a theta plus c. But what is theta? That is 1 over a. Theta is tan inverse of u over a. Okay, tan inverse of u over a. So you can use this thing. You don't have to evaluate this all the time. So it's like a formula you can use. It's like a say integral of say x squared, which you know a formula, so you write it 1/3 x3. So let me write this up here somewhere, so because we are going to use it again and again. So this is in fact 1 over a tan inverse of u over a plus c. Now using that, we can continue this thing, and I think we have enough space here to write it. So this will be 1 over, what is a? A is square root of 3 over 2. That is, if this is a squared, then a is this. Tan, and this is the whole thing. Tan inverse of u divided by this thing. 3 over 2 plus c. Now plug in x here, so this will be, well, if I write it, so that's 2 over square root of 3, this goes up here. Tan inverse of, and 2 goes here, and u equals this, that is 2 times x minus 5 over 2 over square root of 3 plus c. Okay, so that is integral of that expression, I mean the rational function. So you will see that integral of a rational function involves ln when you have 1 over a linear function. It can be tan inverse when it is 1 over an irreducible quadratic, and it might be another rational function when the denominator is like a linear function to some power. So these are the 3 things that you would see. Integral of a rational function in general consists of some rational functions, some ln's, and some tan inverse. Okay, so let me erase this and give you a more general example of this thing. Let me keep this here. So let's write just x minus say 5 something. So I'm just writing things on the fly. X minus 2 times x plus 3 times say x squared plus 2x plus 2. So let me write something which is more familiar. And okay. So we know that this, let's write the partial fraction, find the partial fraction. So that is x minus 2, x plus 3, x squared plus 2x plus 2. And this is a over x minus 2 plus b over x plus 3 plus cx plus d over this. This is not just a constant, it is a linear function. So this up here has should have 1 degree less than this. It should be a polynomial with 1 degree less than this. This polynomial has degree 1, this has degree 0. 1, 0, 2, 1. So that is x squared plus 2x plus 2. Okay? So let's put them to add them. So this is equivalent to that. X minus 5, we'll just ignore the denominator. The denominator here is the same as this one. So I have a times this one, x plus 3 times x squared plus 2x plus 2. Then it is b times this, x minus 2 times x squared plus 2x plus 2 plus this thing cx plus d times these x minus 2, x minus 3. Okay? So, oh gee, I really don't have enough space here. So, okay, so let's see. Let me do it here. So if I let x be, say, oh, there's a plus 3 here. Plus 3. So if I let x be negative 3, negative 3 will kill this one and this one. So if that is negative 3, this left side is minus 3 minus 5 equals this goes away, this one goes away, and this one will be b times negative 3, negative 2, and this one will be 9 minus 3 times 2, 6 plus 2, right? So let me double check. 3 squared is 9, 2 times 3 is 6, and plus 2. So I have minus 8 on this side is 5, and that is 9, 11, it's also 5, right? 9 minus 6 is 3 plus 2, oh, okay. And in minus 5 here I have minus 25b, so b is 8 over 25. So this one I know, this is 8 over 25. Okay, let's set x be 2 this time. So we get rid of this one and this one, we find a. So let x be 2, x2, this one doesn't go away, this goes away, this goes away. I have 2 minus 5 on the left, and that is a times 2 plus 3 is 5. 2 plus 3. 2 plus 3 is 5, well, I write it first. So 3. Then I have 2 squared is 4. 2 times 2 is 4 plus 2. Okay. So 2 minus 3, 2 minus 5 is minus 3, and this is 5 here, and this is 8, 10, right? So and 10 here. So that equals 50A. So A is minus 3 over 50. So this guy here is minus 3 over 50. Okay. So it remains C and D. Okay. Nothing makes this 0. This no real number makes this 0. That's correct to say. No, nothing, because it has complex zeros. Well, I can choose just any number. So if I choose x is 0, then I will get rid of the c. I can find d. So let x be 0. Then I have 0 minus 5 on the left. And a is minus 3 over 50 times 0 plus 3 is 3 times 0, 0, 2. And this one will be plus 8 over 25. 0 minus 2 is minus 2, 0, 0, and times 2. And here I have plus d times 0 minus 2 is minus 2, 0 plus 3 is, so it is minus 6. Oh, okay. Well, I can simplify this 2 and this one will be 25, so this is minus 9 over 25. And this 2 and 2, that's 4 minus 20, and that's plus 25 here, and that is, what was that? That's 4. Okay, 32, so minus 32 here, and this one is minus 6d. So I have minus 5 equals. This will give me minus, I don't know if that's minus, I guess it is minus. There's a minus here, it's plus, and that was 8 over 25, that was minus. Okay. So 9, that's minus 41, I guess, over 25, plus minus 6d. So that gives me d equals, what is it? So minus 5 plus 41 over 25 divided by 6, gee, that is minus 5 plus 41 over 25, that is 25 here. That's minus 125 plus 41, that is 84, no, minus 84. So that's minus 84 over 25 divided by minus 6. 84 is divisible by 6, in fact, and that is 84 by 6 will give me 1, and that is 24, 14, right? 14. So d will be minus, no, there's a minus also here, minus 6d, right? So, I make a mistake. Yes, that's correct. So I will get plus 14 over 25. Let's go with this, correct? 14 over 25. Not enough space. So anyway, so I can check it on Mathematica and see if it's correct. So that is the D. Let me erase this thing. So D is 14 over 25, and now I have to find C. Well, let's see. I can assign any other number to X. x, what? Yeah, if I say x is 5, or 5 is just a big number, because then that's 25, blah, blah, so that is not a good number. Maybe I just give this 1, some small number. So x equals 1. I have 1 minus 5 on the left, and here I have 1 plus, that's 4. So a times 4 times 1, 2, that's 5 again. And this is b times minus 2 and times 5. And then plus c plus d times 1 minus 2 is minus 1. No, 1 minus 2 is minus 1, right? Minus 1, sorry. Yeah. So minus 1 times 1, that's 4. Okay, so let's see. I have minus 4 on this side and 20a here and minus 5b, and here I have minus 4d minus 4c. Okay, so let's plug in these numbers. I don't have enough space here. Let's say 8 over 25, this one I know it, 25. So minus 4 is 20 times a, that gives me minus, that's 60 over 50, that's 6 over 5. 5b, b is this, so 5, that's 8 over 5, minus 8 over 5. And I also have d, d is 14 over 25, so it will be minus 4 times 14, 56, right? So, what do I have here? Minus 4c. So this is 25, and this, if I write 25 here, I have this thing. So I have minus 30 over 25 minus 40 over 25 minus 56 over 25. Gee, oh, no, negative. Is this, that's negative, that was positive, and okay. So that is 70, and so that is let's hope it's correct. Then I have 4c equals 4 minus this. So that's 100 minus that, that is minus 26 over 25. So c will be minus 13 over 50. Minus 13 over 50. Oof. It's not good to write something on the fly. I should have written something and calculated that. But anyway, it's good to know how you do that, even by hand. So let's hope it's correct. I'm not going to do it again. You can. Those coefficients are basically coefficients. It doesn't change the procedure. So I have 3 integrals. One of them is this, minus 3 over 50 x minus 2 dx, then plus 8 over 25 x plus 3 dx, and the last one plus integral minus 13 over 50 x plus 14 over 25 over x plus 1 squared plus 1. Remember, completing the square over there, that's x plus 1 squared, there's 1, so dx. Okay. So, this one and this one, I know what they are. This one and this one, they're Ella. So, let me erase this side. I don't need this anymore. And let's hope things were correct. And I also don't need this thing. I have everything here. And then double check 14, 25. They are okay. So let's say. So this will be minus 3 over 50 ln of absolute x minus 2 plus 8 over 25 ln of x plus 3 absolute plus something. So now our job is this integral, to calculate this integral. So let me erase everything else, and now when you have some linear function here, look at this. Try to come up with a factor of this x plus 1 here. How can I get a factor of x plus 1? So I have a minus 13 over 50. I just write x plus 1 here. Okay. So there's a minus 13 over 50 times this 1 that is added, so I subtract it, so the 13 over 50, right? So if I just write this thing, this is 13 over 50 times x, which is this. Then I have a minus 13 over 50, which is not here. So I have to get rid of it, so I just add a plus. So if this is plus, then I will add minus. And there's also another one left, 25 over x plus 1 squared plus 1 dx. Okay. Now, what is the derivative of the denominator? The derivative of the denominator is 2 times this, right? 2 times x plus 1. So I need a 2 times x plus 1 here. So again, if I multiply this by 2 and divide by 2, so I have a minus 13 over 100, and here I have 2 times x plus 1, and denominator is x plus 1 squared plus 1 dx. This one and this one, when I add them, this is 28 and 13, so I have plus. Let's write this outside. 28 and 13, that's 38, 41, is it 41? Yeah. 41 over 50 integral of this thing, 1 over x plus 1 squared plus 1 dx. I don't have enough space. I guess you can see that. Yeah? I hope so. Anyway, so that is this thing. So what I did was, I had some expression here, some linear function. I just wrote x plus 1 times the coefficient of x, which was minus 13 over 50. Then this adds or subtracts something, so I either add or subtract. In this case, it was minus added here, so I added plus 13 over 50. There was a constant left, 14 over 25, and these two, that's 41 over 50, and this one I need derivative of this up here, which is 2 times this thing. So the first one is simply minus 13 over 100 I have derivative over function. Derivative over function. What is it? It's ln of x plus 1 squared plus 1. Okay. Recall integral f prime x over fx dx is ln absolute fx plus t. Now, so this is f prime, this is f, so it is ln of the denominator, and the denominator is always positive, so I didn't put absolute value here. And the other one is 41 over 50, and that is like this one. That is like a u squared plus a squared, right? And it's tan inverse of u. What is u here? U is x plus 1. So that is times 1 over a. What is a? A is this guy here. So it is 1 over 1 tan inverse of u is x plus 1 over 1. And then I add a c in d. So the integral is this plus this. So this and minus 13 over 100 ln of x plus 1 squared plus 1 and plus 41 over 50 tan inverse of x plus 1 plus c. Okay. So that is the story of partial fractions. And you might have realized, I mean, most often students, the reason they don't like it is because of this, the partial fraction part. Other than that, the integrals are so simple. So it's basically the algebra. The algebra part of this and not the calc part. The calc is finding integrals. So if you know some formulas, like this one, for example, you immediately can find this one. It's just the algebra that sometimes is, well, if you don't have access to some, the internet or some computer programming program like Mathematica, for example, you have to do it by hand. Now, I didn't have enough space here, but my suggestion is if it happens, then just pick some extra scratch paper and do it on scratch paper. Just don't do it in your head. But in general, an integral like this, which has a linear function on top and something which is like this in the denominator, which was an irreducible quadratic, this integral most often will give you ln of the denominator times some constant and a tan inverse. So depending on this, if there is no constant here, you just will end up with this part. If there's a constant here, you will end up with this part and that part. So in general, an integral of a rational function of this type with an irreducible quadratic in the denominator and a linear function in the numerator, you end up with an ln and tan inverse. So if you come up with something else, then something is wrong. Just check your methods and calculations. Okay, so that was the story of partial fractions, and tomorrow I will continue with this chapter, and some other things are in this chapter. So see you tomorrow.